Hey, Mr. Tim, that day I was dreaming about you and your lessons.
Okay.
I thought of this molecule. Can I show it to you?
Sure, please.
So I thought of this benzene ring that there's a CH3 attached to it, but there's also nitro groups attached to it.
Oh, thinking about molecules now, you are low-key in max calculi.
Yeah.
Okay.
So how do you synthesize this molecule?
Interesting. So, do you know what this is called first before we go into this? It's quite interesting. You actually dream about this. Wow.
Yeah.
But I'm not going to use this drawing because this looks terrible. Thank God you are a chem tutor, not an arts tutor.
I'm a chem student.
Right, chem student.
I'm a chem
sure. So what we have here is what you just drawn for me, right? So first things first, I want you to, do you know what this group is called?
Nitro.
Nitro. So we have 3 nitro groups. So we call this a trinitro.
Okay.
And this is actually not in your syllabus, guys, but this is what we call a toluene molecule.
Can you say that again?
Toluene.
Oh, wow.
Okay, so it's got toluene, and we have 3 nitro groups, hence trinitro. Trinitro. Oh gosh, this is quite long. Toluene. And this is the famous acronym TNT. It's an explosive.
The bomb?
Yes, the bomb.
Ooh.
Cue bombing effects. Oh, so cringe, so cringe. Okay, yes, so in today's lesson, we're going to see how, and last week, okay, before I go into that, last week, we actually saw how we created toluene or methyl benzene, right? Now, in today's lesson, we're going to see how a substituent on benzene actually changes how benzene reacts, and it also allows us to add in specific groups at specific positions on the benzene ring. So that will be the focus of today's lesson, okay? Now, we're going to get right into it, and let's go. This is on page 27 of your lecture notes. You can just flip, okay? So, we're going to start with methyl benzene.
Okay.
So, Yap Chen, I want you to tell me, right, looking at this methyl benzene here. So, first things first, of course, benzenes are nucleophilic or electrophilic?
Nucleophilic.
Of course, 6 pi electrons, again. But now, here's the difference, right? Now you have a methyl group. So, do you think, because of this methyl group, do you think methyl benzene is still a nucleophile, or now is it electrophile?
I mean, it's still a nucleophile because the benzene ring is still there, right?
Of course. So your benzene ring pi electrons are still there. It has to be a nucleophile, but the bigger question, stronger nucleophile than plain old benzene or weaker nucleophile?
If my memory serves me right,
Okay.
alkyl groups are electron donating.
Well, someone remembers the stuff. I'm very amazed, yes. Alkyl groups are electron donating, and we donate electrons into the benzene ring.
Yeah.
So if it donates electrons into the benzene ring,
So that increases the electron density of the benzene ring, and therefore a stronger nucleophile.
Okay. So it's definitely going to be a stronger nucleophile compared to a benzene ring. Now, this is where we go into the lesson proper, guys. You're going to see that in today's lesson, we have 2 types of substituents. Some substituents can be electron donating, ED, or some substituents can be electron withdrawing. Just write this down with me, and the words are all on the left. You can just write here with me, more nucleophilic, because you're donating electrons into the benzene ring. Draw the arrow there. And if you're electron withdrawing, as the name implies, you're withdrawing electrons. You suck electrons out of the benzene ring. Now this benzene ring is less nucleophilic, of course, all comparing to your plain old boring benzene. Okay, cool. Now, to be a bit more specific, we're going to focus on what makes a group donating or what makes a group withdrawing. Now, I'm going to go a little bit slow here, so please focus in. If I'm too slow, of course, 1.5 times me on video. No big deal. Now, I'm going to go straight into electron donating groups, and I'll follow through with me, okay? I want you to tell yourself this. If the substituent is saturated, we say it is electron donating, and if the substituent is unsaturated, we say that it's electron withdrawing. Now, Yap Chen, remind me, okay? What does saturated mean? From the first chapter of Organic Chem, Intro to Organic Chem.
Saturated. In the topic of Organic Chem, right? Not KSP, because you just learned that.
Yes, Yap Chen, because you're doing organic now.
It means all the bonds are single bonds.
Very good, yeah. So all the bonds are single bonds. The S here stands for single bonds.
Ooh.
Yeah, that's how you can see it as well. So the S here stands for single bonds. Now, a saturated substituent means this. Now guys, take out your pencil, or take out your imaginary pencil if you're on a bus watching this. Do this with me, okay? Go to the atom that is directly bonded to the benzene ring. Okay, directly bonded. Don't you dare be looking at this or this. We are looking at the atom that is directly bonded to the benzene ring. Box it up for me and focus on it. Now, Yap Chen, focus on this atom that I boxed up, okay?
Okay, I'm focusing.
Are there any double bonds attached to him?
Not that I can see.
They're all
single bonds.
Yes, and that is why we call a saturated substituent. And this is what we call, and you can, guys, write this down with me. electron donating groups. Okay? Now, so Yap Chen, you're going to do the same thing here. Go to the atom that is directly bonded to the benzene ring. Which atom is that?
This C.
Very good. This is the atom that is directly bonded to the benzene ring. Any double bonds on it?
To the O.
Yes. So do we still call this a saturated substituent? No. We call this unsaturated. And we say, now because it's unsaturated substituent, we call this an electron withdrawing group. Okay? Please also do this with me. Tell yourself, because you're withdrawing here, you're sucking electrons out, and if you're a saturated substituent, you're donating electrons in. Cool? Okay, now we have that. Now, of course, we have an exception here that I need you guys to remember, and it is this. So, one more time, right, Yap Chen? Focus on the atom that is directly bonded to the benzene ring. What is it in this case?
It's just an atom.
Yes, there's only one chlorine, right?
Yeah.
Now, saturated or unsaturated?
Hard to tell, man.
Why?
Because you told me to focus on the atom,
Okay.
but you told me to look at the bonds around it.
Okay.
Oh, but yeah, there's only one single bond, I guess.
Okay, so would you call this a saturated or unsaturated?
I guess if you were to follow that line of thought, it would be saturated.
Okay, it is a saturated substituent. You're right. So, would you think it is electron donating or electron withdrawing?
I mean, if it's saturated, it should be called as electron donating, right?
Exactly, but it's surprisingly withdrawing. Make a guess. Why do you think that's so?
Halogens.
Yes.
Halogens are electronegative.
Yes.
Yeah.
And they're the most electronegative elements in your PT, periodic table.
Yeah.
Yeah? Because all the way to the right of your period. So we know that these guys are super electronegative, and therefore, even though you are saturated, your electron, finish up?
Withdrawing.
Exactly. Cool stuff. Okay? And that's why chlorobenzenes or halogen attached to a benzene is always electron withdrawing. Okay, guys? Okay. And that's it. Now, for my quicker students out there, and I know you know who you are, if you're wondering why is it that you're saturated, you're EDG, and you're unsaturated, you're EWG, ask your teachers after class. Okay? I won't explain it here because I think it will confuse the masses. Okay? Okay, moving on. So, of course, like what we said just now, if you're electron donating, then you'll be donating electrons to the benzene ring. The benzene ring is more nucleophilic. I'm going to draw a happy face. And if you're sucking electrons out, the benzene here, or the C6H5 there, is less nucleophilic. And hence, the rate of reaction is quite intuitive. If you are a stronger nucleophile, faster rate of reaction. Weaker nucleophile, lower rate of reaction. Okay. Likewise, this is very important. Start this for me. So of course, you can think about this, right? If your nucleophile is stronger now, do you think your conditions need to be milder or harsher? Stronger or weaker, basically, your conditions?
I mean, your conditions will have to be milder.
Yes, because if you have a much stronger nucleophile now, you need milder conditions for the reaction to start, and vice versa. Okay, guys? Cool. Okay. Now, this is where we move on. Okay, so Yap Chen, you are going to do this with me, and guys, do this as well with me. So, Yap Chen, you're going to tell me, right?
We have a lot of questions.
Yes, there's a lot of parts here. Brace yourself. So, question 11, we have given the following nitration reaction, plain old boring benzene here, and I just want you guys to focus on the temperature here, 55 degrees. Okay? So, predict if the temperature of the following reactions will be higher than, so I'm going to use inequalities, lower than or equal to 55 degrees. Okay?
Okay.
So first things first, this is a plain old boring benzene, 55 degrees. Now, when I attach an alkyl group, remind me again, alkyl groups donating, withdrawing?
Saturated substituent.
Okay.
Electron donating.
Very good. So if I expose all the hydrogens for you guys, focus on the atom that is directly bonded to the benzene ring. You can see that they're all single bonds, hence electron donating. So would you think the conditions are milder or harsher?
Milder.
Milder. So you'd be less than 55 degrees. Okay, I'm just going to write less than like that.
Okay.
So same thing here, C3H7, and I'm not going to do this with you guys. You can do this on your own. C3H7. So very quickly, Yap Chen, do you think this is electron donating or electron withdrawing?
Yep, it's an alkyl group, saturated, electron donating, so it must be milder, so less than 55.
Yes. Focus again on this atom, directly bonded, all single bonds, saturated, electron donating, milder conditions. Okay. I'm going to skip this. You can do this on your own by now. I won't do this with you again. Alright, now this one, a bit more different now. So one more time, Yap Chen. Sorry.
So
to bother you.
Atom bonded to the benzene ring has a triple bond to an N.
Okay.
So that's unsaturated.
Okay.
So it must be electron withdrawing.
Yes.
And if it's electron withdrawing, the condition will be harsher.
Yes. Your electron withdrawing condition is going to be harsher. So would it be less than 55 or more than 55?
More than 55.
Yes. Because now, and guys, write this down with me, it's a weaker nucleophile. Okay? Now, last but not least, let's wrap things off and we'll finish this. Part 5, now it's a chlorine. So again, focus on, try to spot my mistake, okay, Yap-Chen? Saturated substituent, single bond, saturated, of course. So therefore, electron donating.
But this is the exception that you talked about just now, right?
Oh yeah, I forgot. What was the exception again?
Halogens, they are electron withdrawing, right?
Right, halogens. And because they are halogens, they are very
negative.
Yeah, I remember now. It's very, very electronegative. And therefore, even though it's saturated, it will withdraw electrons. Benzene now is a weakened nucleophile. You need harsher conditions, more than 55 degrees. Okay? Alright, I won't explain this answer for you guys. You can do this on your own. I won't do this with you. It's not too difficult. Just write out what we have just said, okay? I won't do this with you guys. Now, so Yap-Chen, before we move on, I want you to look at something quite... Do you see something quite interesting? Look at your products.
Yeah.
Look at all your products.
Let me spot the difference. Well, the NO2 group is placed directly opposite the first three.
Okay.
But for the last two examples, the NO2 is closer to the original substituent, right?
Okay, so the positions are different, right? That's what you're trying to say. The positions are different. Now, I want you to be a bit more precise here. And guys, listen up. This is very, very important. I'm going to teach you on how you look at positions. Do this with me, okay? So we're going to call this carbon 1. All right? This carbon that has that methyl group, because that's where we start from. We're going to call this carbon 1, 2, 3, 4. You can see how the nitro group is on the 4th position. Likewise, 1, 2, 3, 4. 4th position, same as this. What about this one, Yap-Chen? So same thing?
Oh, do I count it clockwise or anti-clockwise?
Oh, that's a very good question. So do I count it clockwise or counterclockwise? So if I count it clockwise, what number is it?
3.
3. And I count it counterclockwise or anti-clockwise, this will be?
5.
5. Which number will you choose? Smaller number or the bigger number? According to your IUPAC naming.
Oh, if you're saying IUPAC, then it's the smaller number.
Smaller. Actually, it doesn't really matter, but I won't go into it. Usually, we always set the smaller number, so 3. Okay? So, same thing, this is the 2nd position.
Okay.
Of course, always remember, guys, if you guys haven't realized, the carbon 1 that you label is always with respect to your initial reactant. Alright? So, this is always 1, 1, 1, 1. Cool? Okay, moving on. And this is where I wrap things up, so bear with me. Deep breath, we're going to finish this up and we'll end this here. Promise you not too much. So this is where we go into directing effect. Now, again, one more time, just tell yourself this. A saturated substituent means, again, you're electron donating, but in this case, you're also 2,4 directing. Now, I want you guys to write this down here.
2,4.
There is no exceptions to this rule. Which means as long the group is saturated, and I don't care whether you're halogen or you're not, as long you are saturated, you are confirmed 2,4. Okay, so you can see here, it encompasses every single saturated substituent, even the halogen, so please circle that for me. Alright, but remember, these guys are electron withdrawing because they are halogens. Alright, again, this is this annoying guy who is always an exception, your halogens. Okay, now, so Yap-Chen, one more time, prove to me how this is 2,4. If we label this 1, okay, so of course, 1 and then 1, this is of course 2. 2. Yes, 2.
Okay.
And likewise, this is 1, 2, 3, 4.
Okay.
Okay. Of course, we don't go count. We don't go anti-clockwise because that will give you 6, right?
Yeah.
1, 2, yeah, 6. 1, 2, yeah, 6. Okay. So of course, you always go for the smaller number. So it's 2,4 directing. Cool. Now, last but not least, unsaturated substituent. Again, multiple bonds. No exception to this rule. The moment you are unsaturated, you are 3 directing. Alright?
Okay.
Okay, Yap-Chen, don't you think this is a lot to take in?
I don't think I can memorize all this.
Neither can I. So I have a very, very quick rule for you guys. If you guys are struggling to remember this, everything is in your DB.
What's DB?
Data booklet.
Oh, okay.
Not your deathbed.
Okay.
Data booklet. Oh god, so cringe. Data booklet, okay? Not deathbed.
Okay.
So you just flip your data booklet and it should be inside. You will see this beautiful table. Everything is in there. So the G here is just the G here, the substituent. And A levels, the data booklet actually tells you everything. So you can see all your saturated substituents here, saturated. All your unsaturated here. So I'm just going to write this very quickly. Saturated, unsaturated, and in the middle, we call them, I'm just going to write them halogens because they're always an exception. Alright?
Okay.
And that's it. So if you're confused about anything, if you can't remember all of the whatever I've mentioned, that's fine. Just focus on this table and you're good to go. Okay? And that's where we'll end this off. And that's where your teacher will step in and guide you through along the way, the rest of the stuff. Alright? That's it, guys, and that is the end of our benzene lesson. That's it, and we will see you in the next one. Okay, bye guys.
Bye guys.
I'm supposed
Oh, we are supposed to